Recording is rolling. It is Wednesday, October 8th. Last couple days, you guys have been collecting data for this lab. And so your setup was this pipe, this screen, a couple title canisters, we pop in different lab weights. You get one spinning and one pulling it in the chat. Just hanging there by its own weight. And the question is, what's the formula that relates all these four variables, this weight, this mass, this speed, this radial size, I split you guys up into different experimental groups. Also, you guys been working on the AP style Reddit. So we'll have all this finished by the end of class today. You guys can send in. That'll be the last points in the grade book for quarter one. Tomorrow, PSAT. So there will be testing in this room. If you want to know if you're testing where you're testing, that Excel file's been on Classroom for about a week now. And then since there's testing in this room, there's relocation from our first four classes. So first four classes, you guys won't show up here. So you guys know where you're relocating? Yeah, I got some stuff there. Okay, so you guys know about relocation? Good. Okay. And then what I want you guys to do for relocations is pull up in your laptop, go to AP Classroom, and work on Unit 2 MCQ. You could probably answer, yeah? Oh, yeah, and I can don't worry about it. Okay. But everybody who's not taking the PSAT, you guys get a really good head start on this. Okay, so you guys can probably answer most of these questions by now, because what we've been doing in class for the last 3 weeks, most of it's those questions. Now, there are some rotational, gravitational questions for kind of get started now. Okay, this Friday is the end of quarter one, so make sure you have all your grades in for all your classes by the end of this week. Because if you turn anything on Tuesday, there's nothing I can do about it at that point. Okay? Oh, speaking of which, I'm still missing some quizzes from you guys. So I wasn't going to hand forces quiz, dynamics quizzes back until I got them all in the first place. So I went ahead and shifted the quiz corrections to quarter two. Right, so I'll just put them on quarter two. I'll come you on anyway. But guys, you got to get me your quiz by this Friday, because if you don't, it just goes in as a zero. And so I gave that to you guys a week ago at this point. Most guys turn that in. All right. So here almost forgot. Okay, so another thing happening this week. Friday, there are junior and senior meetings in the auditorium. So first four periods, breaks down like that. Also picture retakes. Picture retakes are also on Fridays. And so lots of stuff. All right, so let's flip over to this lab.
Picture retakes are this Friday.
Yeah, picture retakes are this Friday. Yeah, I think in the gym, right, where they normally have pictures. Right, so we got this experiment going on. We're trying to figure out what's the relationship among these four variables. Can I link all these variables together in one giant master equation? That's what we're going for.
Someone forgot their calculator here.
Okay. And then let's split you guys up into different experimental groups. So let's start with the spades. Now the spades, you guys were keeping this weight controlled, which by the way, guys, is this weight here equal to the tension in the string? Yeah, same force, right? That would be holding some circle. Right, we'll call that centripetal force. But you guys were controlling that. You guys were controlling the radial size, and you were changing the swinging mass, right, this top canister mass, and saying how did that affect the speed to maintain this setup. Right, so spades. Right, so I think these two over here had spades, right? Right, which would have been these three graphs right here. So we'll start with these three graphs. Now, who thinks they have really good data? Can share their data. All right, so Chase, what was the largest mass that you used?
The largest mass that we used was 202 grams.
202 grams. So I'm put mass in grams here. Right. Now, you guys know we normally use kilograms, but for these graphs, I'm really just care about the graph shape, the relationships. Right, so as long as you consistent with the unit. Now, if it goes up to 202, I'm going to scale it like this. Let's go 50, 100, 150, 200. So you guys know you start all your graphs at 0 in the class and scale linearly. So 50, 100, 150, 200. And then the last mass would be just a smidge bigger than that, so it'll fit. And what was your fastest speed?
It was. You want it in like time over 10?
Yeah. How about time? So centimeters per second.
Okay.
The second last column.
324.
That sounds about right. And so let's go 100, 200, 300, 400. So the speed in centimeters per second Okay. And you guys know what 1 centimeter per second would be. That'd be it moves that distance in 1 second. That might be like a really fast snail. It's like okay, and your guys' cans are flying around. So yeah, 300 something. That sounds about right. So 0, 100, 200, 300, and put 400 up here. So yeah, that'll contain all the data right there. Okay. Oh, I should have had you guys hypothesize. Okay, let's do a quick hypothesis. Because as this mass is getting heavier, 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 how do you think you have to swing this to maintain a constant size circle? Faster or slower? Who says faster? Who says a heavier mass you need to swing faster? Who says a heavier mass you need to swing slower? Okay, so I'm seeing votes on both of those. Well, we're going to find out. Okay. All right, so let's get some data points. All right, what's one data point?
There is. We can do 202 grams
202
and 182 centimeters per second.
and 182. Okay, that's about right here. I got 202 and 182. That's of course grams and centimeters per second. Okay. All right, next point.
182,
182,
194.5.
194, 182, 194. All right, next point.
162
162,
and 207.
207. 162, 207. All right, next point.
132,
132,
217.
217. 132, 217. All right, next point.
112,
112,
234.
234. 112, 234. All right, next point.
82,
82,
292.
292. 82, 292. Okay. Do you have another one?
Yep, the last one is 62,
62,
324.
324. 62, 324. Okay. All right. So, go back and look at that. It's what basic relationship does that best fit?
Inverse.
Yeah, inverse, an inverse relationship. Okay, so just a moment ago when I asked you guys if you make this mass heavier, you should swing it how? If you said slower, that's exactly what this data says. Right? The heavier the mass, the slower you have to spin.
Every graph or just the one?
Yeah, guys, you're making every graph. Okay, so everybody's either has this already or is copying this down right now. Okay. All right. So, yeah, here. If you let's say you had some equilibrium set like where this radius is not changing, okay, and then you make this top canister heavier, and you also swing faster. What's going to happen is that this radius is going to drift bigger, 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 okay, and this bottom weight's going to be drifting upward, okay, which is not what you want. Okay. All right. Yeah. So I definitely see some kind of inverse relationship. Now I don't know exactly how it's inverse, but maybe my first guess is I wonder if it's just a straight inverse. So so I'm going to try to linearize these graphs. Now, linearization, if you can linearize a graph, if you can get it in this form right here, then you can very quickly whip off a slope, just be rise over run, and you come up with a direct equation, and you can know exactly what the relationship is. Okay? So there's two ways to linearize an inverse. You can take the reciprocal of one variable or the other variable. So I could do 1 over v versus m, or what I did here was v versus 1 over m. I'm trying to direct you guys a certain way. This worked out. So I'm going to keep the vertical axis the same. Velocity, centimeters per second. Scales up to 400, just like before. 100, 200, 300, 400. None of that changes. 100, 200, 300, 400. Okay. But the 1 over mass, well, my smallest mass here is going to become the largest reciprocal. So let's do 1 over 62. That's like 0.016. It's it, 0.016. Okay. So how about 0.01, 0.02? Okay. So this is 1 over the mass and 1 over grams. Wait, 60, yeah, okay. Okay, so 0.01, 0.02. That would be pretty close. And then supplies, 15. All right. Chase, you have the coordinates with the 1/mass?
Yeah.
All right. So what's one of these coordinates?
One in
What's one of your 1/mass values?
okay, 100. Point 005.
0.005. That's right here. Okay. And what's the corresponding speed
In
in centimeters per second?
182.
182. Okay, that's right here. So you got 0.005, 182. Okay. So this is 1/grams, and this is centimeters per second. Okay. All right, got a point on the board. All right, what's the next point?
0.006.
0.006. Okay. And is the speed 207?
It's 194.
Oh, yeah, okay, you're right. That was the next one. 194. Right, 194 is right here. Okay. What's the next one?
Next one's 0.0062, so just a little bit.
Okay. And that was 207?
Yes.
Okay. All right, next point.
0.008
Oh, wait.
and then 217.
217. All right, next point.
0.009 and then 234.
234. Okay, next point.
0.01
Right one.
and 292.
292. Okay, and last point.
0.016
16.
and nearly 24.
244. Yeah, that's about what that should look like right there. Okay. Okay, so, what relationship do you think that best fits? Okay, yeah, I'm carrying a nomination for each one of these. Okay. Sometimes it's hard to distinguish between linear versus root or linear versus parabola. Okay. I think we've run into this before also. Okay. Like let's say you start out thinking, I wonder if that looks kind of linear. Okay. And you have just a straight line best fit. You hold your ruler and go straight like that. Okay. Now, one thing that would stand out to me is that there would be a huge sort of like y-intercept right here. And what would that mean? That means if you have 0 reciprocal mass, which is like infinitely large, right? So if you have like an SUV on a string going, that there'd be some exact speed that would come out to. That doesn't sound right. I think I'd have to slow that down more and more. So I think logically, sort of 0 to point, you could empirically run back to the lab and like get more points closer here. Okay? But I think it's not actually linear. You guys, if it's not linear, it probably fits what? Yeah, that root. Okay. I think it would go like this. Actually, that fits pretty well, doesn't it? See that little curve shape right there? Little curve? Yeah. You guess what that is. Right? Like so, if that's true, we haven't quite linearized it yet. And there are two ways you could linearize it from here. You could go v versus the square root of 1/m, and that should linearize it. Or what I'm going to have you guys do is square the v. So v squared versus 1. Here, let me write that down. So if v is proportional to the square root of 1/m, you could graph v versus square root 1/m. That should linearize. Or I could square both sides. V squared is proportional to 1/m, which is exactly the last graph. So I'm going to keep the 1/mass the same. Let's do 0.01, 0.02, and so on. Okay, starts at 0. And then for the speed, now the speeds are getting squared. So it's going to be speed squared and centimeters per second all being squared. Okay. Now these numbers are about to become really big, but that's okay. Because, it's a large number in terms of centimeters per second all being squared. Like, here was the fastest one 324. If I square that, that's like over 100,000.
Yep.
Okay, so the numbers are over 100,000. No, it's a big number, but that's okay. Remember that. So let's go. How about 25, 50, 75, 100, 125? So these will be in terms of thousands. So 0. Okay, so can I just put K per thousand, like 25K, 50K, 75,000, 100,000, and then goes a little bit above 125,000. Right, that will contain all the squared speeds. These aren't even speeds; these are squared speeds. You guys got that? Right. Now this data should linearize, but we're about to find out. Chase, got some numbers?
Yeah.
What's one coordinate here?
Um. 0.005 and 33,233.
33,000. Right there. So 0.005 and then 33,000 something.
Yeah.
Okay. All right. Whatever grams. That's centimeters per second. All collectively squared. Okay. All right, next point.
0.0055. And that's 37,830.
37,000.
Yep.
Okay. Next point.
0.006. 43,000.
43,000. This is probably right back here. Next point.
0.0076 and 47,500.
Next point.
0.009 and 60,000.
Next point.
0.012 and 85,600.
Probably.
Wow.
And then 0.016 and 105,000 was built on.
Just like that. Ooh, guys, could that be like this? It also looks pretty direct. Like it kind of goes through the origin. Yeah, it's your few points a little longer, points a little lower. Yeah, so it looks like a direct relationship. So what you can conclude from that is that the square of the speed is proportional to 1 over the mass. Now, notice that saying proportional to. If you want to make that an exact equation, could you do rise over run and find an exact slope and tag a number and some units to it? Okay. And then that would enable you to say, I can predict exactly what is one speed compared to a mass. Right? Now, the catch is, though, that only works for their set of controls. Like, what radius did you guys have locked in?
30 centimeters.
Yeah, so this only applies to a 30-centimeter radius, and also what was your hanging weight?
212 grams.
Oh, okay, yeah. So some hanging weight, right, some radius, corresponds exactly to that. Right? Now, if you change either one of those, then right, the graph still linearizes for each curve versus one over. Right, so you guys good with that one? Right, so go with the spades. Go with the spades. Right, ready for the next experiment? Okay, next experiment was diamonds, where now we're going to control the mass. Okay. But instead, let's change out the other canister. How about the weight? Okay. Let's do a little hypothesizing before grabbing some data here. Okay. Guys, if you make this hanging weight heavier, how do you think you have to spin it? Faster or slower? A heavier weight, you have to spin it. How many guys say faster? Who's faster? Yeah. Does anybody say slower? Yeah, I think faster does make sense. But then there could be a follow-up question. It's like, how faster? Because, for example, if you triple this weight, should you spin it 3 times as fast? Or maybe faster, but not quite 3 times as fast? Or like more than 3 times, like, I don't know, maybe 9 times as fast. Right? Like, well, we're going to find out with some actual data. Right, so we're on this pair right here. Right, so diamonds. Right, who has some pretty good diamond data? All right, Kathi, what was the largest? What was the largest weight you guys used?
3620.
Okay, so the largest weight in millinewtons was 3620.
Yes.
So let's go up to 4,000. Let's go 1,000, 2,000, 3,000, 4,000. So 0. 1,000, 2,000, 3,000, 4,000. Okay. And these are all millinewtons. That sounds right. 400 grams. Okay. Okay. And then what was your fastest speed?
558.
Okay, yeah, that definitely sounds like centimeters per second, up to 500. So let's go to 600. Let's go 100, 200, 300, 400, 500, 600. So 0, 100, 200, 300, 400, 500, 600. Okay. All right. Now, I think everybody hypothesized that the heavier the weight, the faster you would have to spin it. So it should kind of go up and to the right. But how up and to the right? Is it a straight shot that would be direct to start with? Does it make like a root curve? Does it make like a parabola curve? We're gonna find out. Okay, so what's 1 point?
So 620
620,
and 250.
250. So 620, 250. Right, this is millinewtons and centimeters per second. Okay. All right, next point.
1120
1120
and 345.
and 345. 1120, 345.
And then we have 1620
1620
and 394.
and 394. 1620, 394. All right, next point.
2120
2120
and 419.
419. All right, next point.
What was the last one? Oh, 2620
2620
and 490.
490. Jake, do you have more points?
Yeah, 3120
3120
and 553.
553.
And then 3620 and 558.
58. Ooh, yeah, that looks like what that should look like. Yeah. So, guys, what relationship is that?
Root.
Yeah, you guys think that looks like a root? Looks like a root. Okay. Yeah, if you're not linear for a moment, which you might get like mixed up, then that's like a huge y-intercept. I don't think so. Right? That looks like it kind of does down anyway. Yeah, and yeah, I think as the hanging weight gets closer to 0, the speed would also have to get closer to 0. Yeah. So this definitely looks like it's probably a root, maybe a square root, possibly. Okay. Now, if you suspect a square root, like I suspect b is proportional to the square root of f, I could square both sides and get b squared proportional to f. Okay. And I could graph either one of those, either b versus root f or b squared versus f. Okay. But hey, I remember the last set of graphs we did, I did link it to b squared. And the same opportunity is right here. So maybe let's go with that. Okay. So let's put b squared in centimeters per second being squared here. Okay. As a function of force and millimeters here. Okay. Right, so I'm just going to copy paste the x-axis, scale it 1,000, 2,000, 3,000, 4,000. That's not going to change. 2,000, 3,000, 4,000. Right. Now, if I take the 600 squared, it's like 360,000. Okay. So I'm going to scale the vertical axis. Let's say up to 400,000. Okay. So go 0. Now I know the numbers are really big, but that's okay. We're going to do 100,000, 200,000, 300,000, 400,000. Okay. K kilo could be thousands, right? All right. Keep the got some points.
Yeah.
What's 1 point?
So 620
620
and 62,500.
62,500. Alright, so 620, 62K. Alright, next point.
1120
1120.
and 119.
Okay. 19. You said so you say it again? 1120.
1120 and then 119.
13K. Okay. Guys, that's some kind of interesting. I see. You guys see those 2 points so far? I got look at the first 2 digits of each of those numbers. 62, 62, 11, 11. You guys see that? Right? I bet I'm making a guess. I don't know. I haven't seen the data yet. I'm gonna guess that trend is pretty well gonna continue. Hence that would make a straight line. Right? Alright, let's find out. Alright, next point.
1620
1620.
and 155K.
Ooh, yeah, pretty close. Keep it right in line. 1620, 155. Yeah, 1615. Yeah. All right, next one.
2120,
2120.
and then 175K.
Ooh, all right, so that one dropped off a little bit. Okay, right here. Breaks the pattern a little bit. Okay.
2620
2620.
and 24K.
Ooh, I think we're back aligned again. 20. You said 2620 and 2240K. Okay, next point.
3120
3120.
and 306K.
Oh yeah, that rounds up again. Oh yeah, 3120 and you said 306K.
Yep.
Okay. Yeah, because that rounds and the first two digits match again.
And 3620
3620
and 311K.
and 311K. That's like right here. Okay, 3620, 311K. All right. Guys, does that look linear? That looks linear. Yeah. Zip. Okay, nice. Okay, so you can say then that the speed squared is proportional to the force, right? Where here, because that force directly means the hanging weight. Because is that hanging weight right there the same thing as the tension of the string thing? It's the same force, right? Alright, so now we nail down a pair of relationships. I know the square root of speed is directly proportional to here. I'm gonna just call this the tension force or the centripetal force, right? Is that what that would represent? Right, the force holding something in a circle pattern. The speed squared is proportional to 1 over the mass that's in question that's along a circular path. Okay. But we've got one more relationship to nail down. Are you guys ready for radius? This is the clubs. You guys ready to move on to clubs? All right. So let's do some hypothesizing before I throw anything on the graphs yet. And so let's say you leave these canisters closed. And then here, I'll just roll backwards. Okay, suppose you're swinging this, you're maintaining a circle of some radial size. What if you swing it a little faster? As you swing it a little faster, what happens to the radius? Yeah, it should grow a little bigger, you guys think? Right. And then if I ask it backwards, the same way to get a larger radius, you would have to swing a little faster. Right? I think this graph is going to kind of go up and to the right. But again, same question as before, is like how up and to the right? Like if I double the speed, does that double the radius, or is it something a little different? Okay, so let's get some points. And who has pretty good club data? All right, actually, all right, what was your largest radius? 70? 70 centimeters? All right, so radius in centimeters. Let's go 10, 20, 30, 40, 50, 60, 70. And what was your fastest speed?
Just use those terms.
Huh?
576.
576? Okay. Let's go 100, 200, 300, 400, 500, 600. All right, what's 1 point? 1 coordinate. 590.8. Right, next coordinate. 10, 152. Right, next coordinate. 20, 277. Next coordinate. 30, said 334. 334. Next coordinate. 467. 45, 467. Next coordinate. 6520. 522. 6522. Hey, yeah, but 7 point.
7576.
7576. Oh, look at that graph. Look at that graph. I don't think there's even a question about that. Guys, what is that? Definitely.
Fault.
Yeah, it's definitely this one right here, isn't it? Yeah. Like a sideways parabola, a root. Yeah. All right. Look at that. Guys, all these graphs have been coming out really good today. Same was true for my earlier class too. I think I told you guys that this is one of those labs that if you're kind of messy about controlling the radius or collecting the data, then the graphs don't really make any sense. But yeah, every single one of these graphs has been like right in line with what it should look like. So awesome job at conducting this lab, collecting the data. Right, so if I suspect v proportional to the square root of r, which I definitely do, then let's do v squared proportional r, or I think that would be true. So grand graph v squared versus r. If this linearizes, then that would confirm that relationship. And then you could also make an equation out of that by getting a slope and y equals an x. So let's do v squared centimeters per second squared, and then versus r in centimeters. So I'll keep the radius axis the same as before. Go 10, 20, 30, 40, 50, 60, 70, 0, 10, 20, 30, 40, 50, 60, 70. Okay. And then for the speeds, if I take 600 squared, that's like 360,000. Let's go 100,000, 200,000, 300,000, 400,000. 0, 100,000, 200,000, 300,000, 400,000. Okay. All right. You got some coordinates. What's one coordinate? 5 and sorry, say that again. 8,000. Okay. What was the original speed over here? The original speed was what? Was what? 90.8. If I spread that, yeah, 8, okay, yeah, 8,200. That's about right there. All right. Next point. 10, 23. All right, next point. 76,000. Next point. 112,000. Next point. 45 to 15. Next point. 60 to 72. Probably right there. And last point. 332. Right there. Oh yeah! Oh yeah! Look at that! That is a straight line. Straight line. You could pick 2 points on the line, do rise up or run, and get b squared equals. Here, guys, can I call this slope? You guys can calculate a slope, right? Just right through the run. If I put points in there, can you guys say v squared equals whatever the slope is times the radius? That could be an exact equation, couldn't it? Guess that. Okay. But again, that applies specifically to whatever math canister they had flying around, also whatever weight canister they had hanging out. So in general, for everybody's lab, I can say b squared is proportional to r. Okay. Huh? Okay, yeah, let's do it. Probably send it to you. All right, so guys, let's so here I'll finish this lab off in this corner up here. So what we want to say, actually here, how about down here? You got some space down here. So I have three relationships, three proportional relationships. So we got b squared proportional to the force, b squared proportional to 1 over the mass, and b squared proportional to the radius. Can you guys put that all together? Say b squared is proportional to, so I have a big old fraction. Okay. Here, can you guys finish off that fraction in terms of the last 3 pages? Proportional to force. Right here. Got force. Proportional to radius. That's right here. And proportional to 1 over the mass. Isn't that like that? Is that true? Okay. But this is for all the graphs. Guys, all the graphs conspire together to create this giant proportion. This is still a proportion. If I want to make it equal, I'd have to go get all the slopes and put them together. Right? Okay. But then we kind of mix and mash in apples and oranges. Okay. All right, last thing. I want to do one more thing here. One more thing. I want to solve for this force right here. The F. Okay? Because from here on out, going forward, I want to know what is this, and guys, what kind of force am I calling this again? I know it's a weight or a tension. Centripetal. That's what I'm looking for. Guys, so when something's moving on a curved path, what force do you need? We'll call it centripetal force. What is that in terms of the mass of the object moving in a circle? What is the radius of that circle, and how fast is it going? Can you guys solve for force? Can you say force? Well, at least proportional. Proportional to what? Guys, go ahead and finish this off. Proportional to what?
That's squared. Under the curve divided by r.
NV squared over r. Yeah, that's it. NV squared over r. Right there. Yeah.
How does this thing work?
Well, here, I can show you the inputs. Well, you need a string for that. I think that disappeared somewhere.
I was ready.
Yeah. All right. So,
Hey.
right. So I got this poster summarizes everything that you guys just did. Okay. And then here's the conclusion we're coming to. Is this right here? So if you have this mass swinging around in this weight, which is equal to this tension, providing the force, right, in this speed, and then this radius curvature for the circle, put it all together. Turns out you can actually drop the proportion, make it an exact equation. This turns out to be an exact equation. And you can try this too. So all of you have a bunch of data that you've been collecting over the last 2 days. I bet you could take any one of those rows because all your data looks really good. You guys gave me some really nice looking graphs. I bet you could take your swinging mass times the speed squared divided by radius of curvature, and I bet that tells you exactly, or pretty close, what the force was, right? Whatever the hanging weight was. You guys see it? Okay. And on the AP equations, you guys remember AP equations? We've been coloring in these, we've been going along. Well, AP doesn't exactly spell that out, but they have a very similar one. You guys see this here? It says centripetal acceleration is v squared over r. Okay. Isn't that the connection between force and acceleration anyway? You just divide by mass. Okay. So that's going from this box to this box. So centripetal force is mv squared over r. But if you divide out the mass in question, you can get centripetal acceleration as v squared over r. Okay. Hey, you guys have your driver's licenses, right? You guys driving? You guys get on I-95, and then let's say you hit one of those off ramps, and you start going around. Just some off ramps, big loop and circle. Okay. Suppose you exit a little bit faster, maybe you're going like 50 miles an hour. So slow down. Okay. And you're going around a loop. Okay. Does it feel like you're kind of pushed to the side? Can you feel it? Like you're pushed to the side? Okay. Now, if you watch that Vsauce video, you guys know that really you're trying to move in a straight line. You for slow motion. Maybe the wall of the car, your seatbelt is pulling you to the side, right? Or keeping you on a circular path. Okay. But could you sort of quantify how much you feel like you're thrown to the side? Sort of in terms of Earth G's, like, oh, it feels like gravity shifted and pushing me to the side. Is that what it feels like? Okay. That's what this is right here. So here, let's say you were going at like 20 meters per second, and the radius of curvature on that off ramp is like 80 meters. But let's see what that would be. If you're on 20 meters per second, and this curvature is like 80 meters, can I do v squared over r? And the acceleration is like 5 meters per second squared. You guys see that? Guys, how many g's would that be? Guys, 5 meters per second squared. How many g's is that? Half a g! Yeah! Because 1 g is 10 meters per second squared. 9.8, 10. Okay? So if you do v squared over r and you get 5, doesn't it feel like you're being pushed to the side like half of Earth's gravity? Yeah, that's exactly what that would mean in that context. Right, you guys get that? Okay. Now, so now we have a way to get force to keep something in a circular pattern or centripetal acceleration. And either way, this force or this acceleration points to the center of the circle. Do you guys see that? Isn't the string tension pulling to the center of the circle? Or in terms of if you're going around on the off ramp, right, you feel like you're thrown to the side. It's always towards the center of the circle, like the walls of the car are pushing in. Okay. Now, this is for a linear tangential velocity. Because, guys, can you quantify this v in like meters per second or in a lot of centimeters per second? Okay. But for some context, especially if you have like a turntable or a giant rigid rotating circle, right? Sometimes it's actually easier to quantify centripetal force with centripetal acceleration, not in terms of linear speed, but in terms of angular speed. And for that, I should break out a turntable. It's about to be turntable time. Here, let me play you guys a Paul video, change things up a little bit, and break out a turntable. Yeah, listen to Paul. It's Paul time.
Riding on a merry-go-round. When do you travel faster? When you're on the outside horse or on the inside horse? Or do both horses travel at the same speed? Well, it turns out there's two kinds of speeds there. And we can see that with this little make-believe merry-go-round. If I draw a line, rotate the merry-go-round, we see that all parts of the line are traveling the same RPMs, revolutions per minute, yeah? But how about the linear speed, like in miles per hour? Outside or inside going faster? Well, let's put some people here. One here, one here, one here. These little pennies represent you, huh? I think you can see the outside part is traveling faster. If I whip it up a little more, yes, the outside one flies off. A little more. Ah, so it's the inside one that is going slower. That's physics. Yay.
So, guys, when you turn in your lab, okay, so you guys have all the data you've been collecting the last 2 days. You guys have all 7 graphs, which we definitely put together today. And then for AP, you guys know that AP write-up. So I helped you guys out with that the other day. The other part you need, so I'm looking for the full procedure. I helped you guys with the setup and the procedure. The analysis is just the 7 graphs that we did. And then your conclusion, well, if you want the master conclusion, it's this right here. F equals mv squared over r, right? Or if you just do it for your own lab, that's okay too. So you can say either v squared proportional to r, or v squared proportional to 1 over m, or v squared proportional to f, right? That could be your conclusion right there, right? If that was your lab. Couldn't that answer your question? You had one of those 3 questions, didn't you? So your conclusion is one of those 3. Okay? Now, what you guys just saw, Paul in this turntable. Okay, so let's say I get what you guys down here. All right, so I got Lincoln, I got Roosevelt, and I got Washington over here. All right, say I give them all a spin. Ooh. All right, so going around. All right, so let's think about some kinematic values. And what would they be in linear sense, and what would they be in a rotational sense, or I might call it angular instead of rotational. Okay. So let's start with distance. Guys, how far is Lincoln moving right now? No. Nowhere. Isn't Lincoln just getting dizzy, but he's not really moving anywhere, right? Okay. In terms of distance. How about Roosevelt? Guys, is Roosevelt like driving around a pretty good distance? Okay. So if he was driving around a car in a circular path, isn't the odometer adding up like some distance? Okay. Now what about Washington out here? Guys, is Washington traveling the same distance or a further distance than Roosevelt? Further. Now, see, he's twice as far out. Guys, if he's twice as far out, what do you think his circular distance around is? Do you think it's 2 times as far?
No.
I think it's 4 times.
Okay. How about this? Guys, what is the formula for circumference of a circle? That's what we're talking about, right? Circumference? 2 pi r. Guys, 2 pi r. Okay. Now, guys, look at this one here. This one's going to be really helpful. This is going to connect linear type motion to angular motion or rotational motion. Okay. So, guys, how many degrees is it around a circle? 360 degrees. Okay. But there's different ways to quantify that. You could also call it 1 revolution. How many radians is it around a circle? 1. Here, guys, let's back up a little bit. Okay. Let's say I take a string right here. Can you guys imagine my string? You see it? And it stretches out to radius r. And start wrapping that around. It gets to right there. Do you guys see theta equals 1 radian is shown? You guys see that? Okay. So that's if I take 1 radius and I stretch it around and it goes that far. Okay. And then I take that. There's 1, 2, 3, 4, 5, 6. That doesn't quite do it. There's a little more. 6 point what? 6.28. Because that's 2 pi. Guys, that's what this says right here. So if you make exactly one trip around the circle, that's 2 pi radians, and because this has to be in radians for this to work. You can't put degrees in here. Can you put degrees in here? Not to this equation. I'm trying to relate how far have you gone around in a linear sense, if I'm adding up the number of meters, to how far is the whole turntable turned. But it has to be in radians. 2 pi r is one circumference. Hey, circumference equals 2 pi r. You see that? Right. Now, what's really nice about this formula is that you don't necessarily have to go exactly one circumference. You're not locked into one rotation all the time. You can go any amount. Like if you just want to go 1 radian, you can go that far. Do you guys remember what 1 radian is in terms of degrees? 360 divided by 2 pi. Is that like 57 degrees? You guys remember that? Okay. That's here, that right here. That's a 57 degree angle right there. 57 degrees. Right? 57 degrees. Okay. Okay. How about this? Guys, what's the rate change of location called? Velocity. All right, so let's take a rate change. And the rate change of how far something is turned is how fast it's turning. Look, it's angular velocity in radians per second times r. Okay, so do you guys see for both of these, how far you've gone or how fast you're going is just very simply proportional to your distance from the center. So that brings us back to these 3 presidents right here. So now Lincoln, he's not moving anywhere, and he also has 0 speed. Like if I point a radar gun and read 0 meters per second. Right? But Roosevelt has gone some distance around, and Washington has gone further around. How much further? He's twice as far out. So that's 2 times as far. So Washington has gone twice the distance of Roosevelt. So if Roosevelt drove around, took him 3 miles, it takes Washington 6 miles because that's twice as far. Because it's twice as far out. Okay. So factor 2 on that r is factor 2 on that s. They both gone around 2 pi radians. Go around. Okay. Guys, what about speed? What if I put a speed gate right here? And Roosevelt speeds through, zoom, and it reads so many meters per second. And then I do the same speed gate for Washington. Like, zoom. Guys, how many times is fast? I mean, he's still twice as far out from the center, right? How many times faster is Washington going compared to Roosevelt? The answer is right here. So do they all have the same angular speed? They're all doing the same turns per time, right? Same angular speed. But if you're twice as far out, that means you're going how many times as fast in a linear sense? Twice as fast. You see it? It's a direct relationship. Okay. Now, what about this last expression? If this is displacement, this is velocity, this one must be what? Acceleration. And to have an angular acceleration in radians per second squared, what would this turntable have to be doing? Have to be speeding up spinning, or if I let it slow down by friction, slowing down spinning. But it would have to be changing its rate of spinning, wouldn't it? Either speeding up or slowing down spinning. Okay? And that's what this alpha or this A refers to. So this A is like a tangential acceleration, not actually centripetal. So we are out of time. So make sure your labs turn to the grade tray. I'll be grading that for you guys, and well, I'll see you next time I see you.